All right, so we're going to look at something called the ion product constant for water. And it's basically a form of KEQ. You'll see as we move forward, there's lots of different versions of this KEQ, right? We started with KEQ, then we looked at KSP. Now we're going to look at KW. And there's one specific for acids and bases as well. So they're all based on the same principle of like an equilibrium constant. So where does this come from? What exactly are we talking about when we are saying an ion product constant for water? Well, occasionally water molecules will collide with enough energy to react. Okay, and when they react, what they do is they ionize. They break apart into their separate ions. So when this happens, an H plus ion is transferred from one water molecule to another. This reaction is called the auto-ionization of water. Now the link below doesn't work, but I've found a different video that actually diagrams out and explains this process quite well. So you'll notice there's a second video link in today's Edmodo post. So if you can pause here now or at any point and check that out. It's just a short, I think 4 or 5 minute video. And he shows how water breaks up in this process. And it just gives a better visual understanding of what's happening. So check that out. Okay, but basically what this looks like is we've got two water molecules, okay, and they're going to have a collision right here. That means they're colliding. And we've got a reversible reaction here. And what happens is one of the H plus ions, when the collision happens, is attracted to the slightly negative end of the water molecule, the OH negative end, right? Because if we look at water, we've got, not OH, sorry, the O. We've got negative, positive, positive, because it's polar. So that attraction actually attracts a hydrogen over. And when that hydrogen comes over, it joins and it makes this H3O plus, which is the hydronium ion. And that leaves your other water molecule like this, with just the O and the H, which is the hydroxide ion. Okay, so that's what really is happening in the collision. Just the H plus from over here zips over here when they collide. And that's due to the attraction of positive to negative. Okay, so we get this ionization. We've got a positive ion and a negative ion based on the collision of these two water molecules. So what we do to simplify this is instead of using this hydronium ion, we just replace that with the hydrogen ion when we show the process. So we just show, this is sort of like a simplified look at it, is water is ionizing into H plus ions and OH negative ions, right? It's dissociating, breaking apart. Okay, well, only a small fraction of water molecules are ionized in this way. So for this reaction, because we've got a reversible reaction here, this process is happening in both directions and will reach an equilibrium, right? The rate at which it's ionizing is equal to the rate at which these ions are coming back together to form water. So we can use the equilibrium constant expression, KEQ, and we can write it out like this. Products, the concentration of the products multiplied divided by the concentration of the reactants. Okay. Okay, so however, if we look back up at this reaction, water is liquid and these are our aqueous ions in solution. So we don't include a liquid in our KEQ expression, right? Because the concentration of a liquid is constant. So because water has a constant concentration, we can leave it out of the expression. So our KEQ expression just becomes H, the concentration of H plus ions multiplied by the concentration of OH negative ions, and it gets its own special symbol because it's specific to this process. So we call it KW, and it just looks like this: H plus and OH negative. And it's always these two ions, right? Because that's all that water has in it. So this KW ends up being called the ion product constant for water. So the W just makes it specific to water. So it's still an equilibrium constant, but it's specific to this ionization of water. So because only a small amount of water ionizes, okay, so it's not all completely ionizing, right? Just a small amount of it is just the water molecules that have enough energy to collide in this way. The concentrations of the H plus and the OH minus ions in water is really, or I should say are, really small. Okay, so if you see here, this is what the concentrations are, right? So we know that when water breaks up into H plus and OH negative, it's in all of this is in a 1:1:1 ratio. So whatever your concentration of H plus is, it's also equal to the concentration of OH negative. Okay, so the concentration is 1 × 10⁻⁷ moles per liter. Okay, so for both of them. And so because they are formed in pure water, they're in equal concentrations, 1:1 ratio. So therefore, if this is our KW expression, if we plug those concentrations in for each of those two ions, what we calculate is a value for KW. And the value is 1 × 10⁻⁴ when you multiply these two together. Now this is the value for KW as long as your temperature is at 25 degrees Celsius. If the temperature changes, the KW will change. So you get a higher KW at higher temperatures. And the reason for that is because at higher temperatures, the molecules are moving faster and they have more kinetic energy, so they're going to collide more frequently. So you're going to get a higher concentration of the ions. More of it will ionize at a higher temperature, right? Higher concentration of ions would mean a higher value for KW. At lower temperatures, you're going to get less ionization because the molecules of water have less energy, less motion, fewer collisions, therefore fewer ions are formed. Okay, so this value is specific to this temperature, but this is the value we'll always use unless otherwise stated. Okay, so in an acidic solution, the reason why this KW expression is important is because it helps us determine whether something's acidic or basic. So we know in acidic solutions, we have this H plus ion, right? Whereas in most basic solutions, you have a concentration of the OH negative ion, the hydroxide ion. So if we're using this formula, if we find that our H, like this is the concentration in pure water, right, of the H plus and the OH negative. But if we're not dealing with pure water, these concentrations change. So if you end up getting a higher concentration of H plus than OH negative, and I'm just going to flip over to the next page here for a second. So if our H plus ion concentration is greater than 1 times 10 to the negative 7, then we have an acidic solution. And that would also mean that the H plus ion concentration is higher than the OH negative concentration. So this would, the other reverse, or the other thing going on is that the OH negative concentration is less than 1 times 10 to the negative 7. Okay, because the two values, the concentration of the H plus and the concentration of the OH minus, have to always multiply to that 1 times 10 to the negative 14. So if you end up changing this value, the other value has to also change to adjust. So if one increases, the other decreases, and vice versa. In a basic solution, what you'll see is a higher concentration of the hydroxide ion. So the OH negative concentration is greater than the H plus concentration. So in this situation, the OH negative concentration is greater than the 1 times 10 to the negative 7. And of course, the other situation would also be true, like we stated above. And the H plus would therefore be less than. Okay, so in a solution, if your H plus ion concentration increases, then the OH negative concentration decreases, because we know that when you multiply those two concentrations together, it has to equal 1 times 10 to the negative 14, which is the ion product constant for water. So they are always working in opposition. If one goes up, the other goes down, and vice versa, to always maintain this constant value. So let's do some problems. How would this relate to some questions? So here's a potential problem you could come across. If you have an H plus ion concentration of 1 times 10 to the negative 5 moles per liter in a particular solution, determine the concentration of the OH negative determine the concentration of the OH negative ion in the solution, and then decide if the solution is acidic or basic. Note, we can always substitute in this value for Kw, okay, this 1 times 10 to the negative 14. So let's start by writing our Kw expression, which would be this here. Just multiplying the two ion concentrations. Now we know this is what Kw is equal to. And we're just going to assume we're at 25 degrees Celsius because we're not told otherwise. And we are told that the H plus ion has a concentration of 1 times 10 to the negative 5. So we just need to solve for OH negative. So we're going to divide both sides by 1 times 10 to the negative 5. And when we do that, what we get is an OH negative concentration of 1 times 10 to the negative 9 moles per liter, right? You can always just subtract your exponents in this particular case, right? So negative 14 subtract negative 5 is negative 9. So there's our OH negative concentration. So now we're going to compare those two ion concentrations to decide whether the solution is acidic or basic. So over here, let's put, therefore, the solution is acidic. And the reason it's acidic is because we have a higher concentration of H plus and a lower concentration of OH minus. So I'll say because H plus concentration is greater than the OH negative concentration. So that's also an important part to our answer. Okay, let's try one now where we are given the hydroxide ion concentration. So we're going to go about this in the same way. Here is the concentration of the OH negative ion, and we're asked for what the concentration of the H plus ion is, and then again to decide whether it's acidic or basic. So I'm going to plug in Kw. I'm always going to use this value unless told otherwise. So this is what I'm looking for, and I know OH negative is this. So I'm going to divide both sides by 1 times 10 to the negative 3. So that will give me an H plus ion concentration of 1 times 10 to the negative 11 moles per liter. Okay, so now that we know our two concentrations, we have a very small or even smaller value for H plus and a larger value for OH. So in this case, or OH negative, I should say, in this case, our OH negative concentration is higher than our H plus concentration. So that would give us a basic solution. So therefore, the solution is basic because OH negative concentration is greater than the H plus concentration. Okay, so let's look at something a little bit different. So these ones are pretty straightforward to solve. Now we're going to look at a solution where we have some other solute dissolved, okay? So here it's saying, what is the H plus ion concentration in a solution of 0.03 moles per liter of sodium hydroxide? Is this solution acidic or basic? Okay, well, how do we figure that out? Here we have a solute, and that solute contains the hydroxide ion, right? Sodium hydroxide. Okay, now sodium hydroxide will dissociate into the sodium ion and the hydroxide ion, and this all occurs in a 1-to-1 ratio. So if the concentration of sodium hydroxide is 0.03 moles per liter, that means that you also in this solution have an hydroxide ion concentration of 0.03 moles per liter. So we can use that value in our Kw expression. Okay, so I'm going to put Kw equals H plus ion concentration times OH negative. And we're going to use this value for our OH negative ion concentration because we know it's got to be the same as that concentration. So I'm still going to use my same Kw value, and this time I'm solving for H plus, and I'm plugging in this particular concentration here. So I'm going to divide both sides by 0.03. And that's going to give me an H plus ion concentration of 3.33 times 10 to the negative 13 moles per liter. Okay, so that's one part of my answer. The next part is the solution acidic or basic? So I'll say, therefore, the solution is, well, here we have an extremely small value for H plus concentration, and we have 0.03. So this is only, if we're talking about scientific notation, this is only times 10 to the negative 2. So quite a significant difference in concentration here. So we're going to say this solution is basic because the OH negative concentration in this case is much larger than the H plus ion concentration. Okay, one more. I guess we did that part already. So let's try something a little bit more involved. We're going to calculate the hydroxide ion concentration in a solution of hydrochloric acid, or HCl, made by dissolving 0.37 grams of HCl in water to form a 250 milliliter solution. Okay, so a few things we need to sort out here. First of all, hydrochloric acid is a strong acid. So if you remember back to a previous lesson, strong acids completely dissociate in water. So it all dissociates. And we can represent that with this expression here. HCl dissociates into the H plus and the Cl minus ion. Okay, so this is important because we can then, if we figure out what the concentration of the hydrochloric acid is, right, based on this, how many grams in a 250 milliliter solution, whatever the concentration of HCl is, will also be the concentration of the hydrogen ion. Okay, so step one is determine the concentration of the HCl solution. Okay, so our first step would be, we're in grams of HCl. So in order to get a proper concentration, we need to get that into moles, so we can get our concentration in moles per liter. So 0.37 grams of HCl. I'm going to put grams here and moles here. In 1 mole, this would be our molar mass. Okay, so the molar mass is chlorine's mass plus hydrogen's, which would be 36.46. So grams cancel, and what you get there is 0.0101 moles. Okay, so once we know that, we can use C equals N over V to get the concentration. So I'm going to take my number of moles, and I was told in the question the solution has a volume of 250 milliliters, which is 0.25 liters. So the concentration works out to, 0.0404 moles per liter. Okay, so if we have that, now we know that the concentration of H plus ions in solution is equal to the concentration of the HCl. So therefore, the H plus ion concentration is what we just calculated. So now, step 2 is use Kw to determine the hydroxide ion concentration. Okay, and this would be just like what we did before. Okay, so I'm going to plug in what I know. Well, I know Kw is always this, assuming my temperature is 25 degrees Celsius. I'm not told otherwise, so that's what I assume. I'm going to put in a hydrogen ion concentration, and then I'm going to solve for the hydroxide ion concentration. So I'm going to divide both sides by this, And that will tell me that the hydroxide ion concentration works out to 2.48 times 10 to the negative 13 moles per liter. Okay, so that's what I was asked to find. Now, we do know that like HCl is hydrochloric acid. So we're obviously dealing with an acidic solution. So just compare your hydroxide ion concentration to your hydrogen ion concentration and realize that this is an extremely small concentration for OH negative, and we have a much, much larger concentration for our hydrogen ion. So just further proves that this is an acidic solution. Okay, so now that you're done some examples, you're going to work on, there's two kind of little assignments that go along with this, I think called Worksheet 3 and Worksheet 4. I attached them all in one document, so you can try some of these questions out yourself.